Hello guys, so this is the video editorial for a problem in Starters 18, Palindromic binary numbers. So before starting, a brief introduction about myself. I am Istasis Mishra. I'm a fourth year undergrad at IIIT Hyderabad. I have been to ICPC regionals twice in my first and second year and represented India in IOI 2018. So without any further ado, let's just get into understanding what the problem is asking for. So yeah, you are given an integer n, and what you need to do is find like a few integers that sum up to n, like s1 plus s2 plus s3 equals n. You need to find these three integers, and these three integers need to have some special property, which is if you write them in binary, they must be a palindrome. So yeah, as an example, 107 is a valid number, because if you write it in binary, it turns out to be 1101011, right? So this is a palindrome. Yeah, so a good way to approach this problem, and yeah, you can use at most 12 integers of this form. Okay, n can be, so you can see the constraints, n can be up to 1000, the number of test cases can be up to 1000. So yeah, now coming to how do you solve this. So it's pretty simple. What you need to do is find numbers of the form that start with a 1 and end with a 1. It doesn't matter if they are odd length palindromes or even length palindromes. This will always be a palindrome, right? Because 101 is a palindrome, 1001 is also a palindrome. So numbers like 1, 3, 5, then any number of the form 2 to the power n plus 1 will be a valid palindrome of this pattern, right? Because 2 to the power n is 1 followed by n zeros, right? And if you add 1, so in the end it will be 1, right? So keep all the numbers as 2 to the power n plus 1 in an array. So 1, 3, 5, then 4 plus 1, right? Then 8 plus 1, 9, then 16 plus 1, 17, and so on till 513. You don't need to go beyond that, because after this it will be 1025, but n is at most 1000, right? So since n is at most 1000, you don't really need this number at all, right? Because if you are writing this as a sum of integers, you do not need a sum that is larger than n. So si is less than equals n, right? This must be true. So these numbers, so one thing to observe is that you can treat this as denomination of coins, let's say. So a common problem which has a standard problem goes like this, that you have coins of, let's say, 1 rupee, 2 rupee, 5, 10. What is the minimum number of coins or notes that you need to use to make a specific sum, right? So what do you do here? You use a greedy approach, right? To make 27, you will first take 10 and 2 of them, then you will take 5 because you can take it. So 10, 10, what is remaining, right? 7. You cannot take 10 anymore. You need to take 5 now. So you take a 5, what is remaining? 2. You take that 2 and you are done, right? This is the minimum number of coins to make up 27. So think about this in terms of that problem. So these are all your coins. So this approach is known as the greedy approach, because you greedily take the largest possible number that you can take, and then you just include it in your sum. So there are quite a few problems with this. First, we need to prove that we'll need at most 12, right? So we'll need at most 12 integers. So that is a constraint that we have. We have to still prove that taking the maximum possible integer from this array every time will give us 12 integers at most. Why is that? What is 2 into 2n plus 1? What is this value? This is 2n plus 1 plus 2, right? So you subtract 1 from it to get 2n plus 1 minus 1, right? Yeah. So let me just move this. Yeah. So this is your next number in the array. So this array can be written as a recursive sequence where ai will be equals 2ai minus 1, right? Except for 1, right? Except for 1, this always holds. Because 3 into 2 is 6 minus 1 5. 5 into 2 is 10 minus 1 9. 9 into 2 is 18 minus 1 17, and so on. So 1 is the only exception to this rule. Apart from this rule always holds, right? Because 1 is not 2 to the power n plus 1. 1 is not a part of that. 1 is the only exception. 1 is just 2 to the power 0, right? So if you do 2 into 2 to the power 0, you get 2. But that is not true. Apart from 1, every other number follows this rule. Okay. So you can see that if you double the number, that is greater than the next number, right? So if you use, let's say 5 right now, okay, let's say the maximum number is 1000, right? The maximum number is 1000. If you can use 513, you will use it. But after using 513 once, you will not be using 513 again, right? Because if you do it, that means that there is some number that is 1026. That cannot exist. Okay, so after using 513, you have a number, you have some number x less than 513, but greater than, let's say, greater than or equal to 257, right? 256 plus 1. This is the number before 513. So if a number is between this range, once you use 257, you will not be able to use 257 again, because what is 2 into 257? It's 514. But you know that the number is less than 513, right? Because you have used 513 once. You can, it will never occur that after using once, you have to use it again. So after using 513 once, you know that you have to use 257. You will not use 513 twice. Similar way, 257 also you will use once, because if you use it twice, that means originally you had a number which is greater than 513 and you did not use 513, right? So by that logic, every number here you will be using once and only once. And how many numbers are here? This is 2 to the power 9 minus 1, right? 513 plus 1, yeah, right? 2 to the power 9 plus 1, and this is 2 to the power 0. This is 2 to the power 1 plus 1. So 0, 1, 2 up to 9. So there are the size of this array is actually 10, right? So you will be using at most 10 numbers, but then 1 does not follow this rule. So after using 3, you may need to use 1 twice. 1 is the only number that you may need to use twice. You will not use it thrice. Why not? Because then you can just use 3, right? So try to think about this. You will use 1 is the only number that you may use twice, but not thrice. Because if you use 1 thrice, that means the number was 3. But you could have just used 3. So 1 is the only number that you use twice. So at most, how many numbers will you use? 11. Right? So pretty simple problem. It's cakewalk to easy. I'll just show the implementation once to actually explain that this problem is not that difficult and it is actually as easy as it sounds. So if you look at the code, this is the code that I have written and gotten accepted as well. So just look at the solve function. The rest of the things don't matter, okay? So you take n, right? this temp is not required, right? I make two vectors, the answer vector, which will be my list of denominations that I take into account, and my din vector, which is the denominations, which is 1, 3, 5, 9, 17, 33, 65. You can write it manually, right? It's a size 10 array. So I goes from the largest number to the smallest number. If denomination I is less than equals n, that means, so if it's less than equals n, if the current denomination is less than equals n, I put that in my answer and decrement n by that value. And in the end, if I use 1 once, like I need to use 1 twice at most, right? But if I use 1 once and I see that n is 0, then I'm done. But if I see that n is 1, if 1 is remaining, so if this is one more condition that you need to add, okay? If n, that means n is 1 till now, so I just answer that pushback 1. Then I just print the answer in the output format that is in the problem statement. So first I need to print the size of my vector answer, and then I need to just print the elements in the vector, and that is it. It's very simple, right? Common mistakes that people made were thinking that 2 to the power n is a palindrome in this logic, that 2 is equal to 1 0, right? That can be written as 0 1 0. So then every power of 2 is basically a palindrome that way. But in the problem statement itself, it's explicit. It's not explicitly mentioned that trailing zeros are not allowed, but it's commonly granted that if in the problem statements it's not written that trailing zeros are supposed to be considered, then you do not consider them. Otherwise, the problem is also too easy, right? It's too easy. So yeah, I hope you enjoyed this solution, and I hope to see you in my future editorials as well. So yeah, I did not change the board, so yeah, I'll just explain it again. 2 is 1 0. People were thinking that you can add a trailing 0 and make it 0 1 0, and then you are done. So like this is a palindrome, but this is not. Trailing zeros are not allowed. In a problem statement, if it explicitly does not mention that trailing zeros you are supposed to take into account, don't take it into account. So yeah, I'll just end it here. Thank you for watching, and until next time.